In the previous lesson, we have discussed the bigger picture of the course without really delving into why this study of probability is so vital and why it is important to the advancement of science. Let's do that. And now, by looking at some of the examples, like let's see an example. Suppose that Delhi State Committee Delhi State Committee for the fun of student claims that the average concerts attended yearly by the student is to right. Then suppose we take a random sample of about 500 or say 50. Let's not take bigger number. Let's say 50 Delhi student and determine that average number of concerts attended by the students, right? To to answer this, we actually take a picture to it and uh, so we take the average and like let's say it's 1 4 3 2 and dot 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 150 and it comes as 3.2. Let's suppose that it comes as 3.2 concerts per year, right? Then that then begs the question that if actual population average is 2, if the actual average is 2, then then how likely it is how likely it is that we would get the probability or the average to be 3.2 concerts, right? This question arises, what do you think about this? Is it likely or not likely? If the answer to the question is ultimately not likely, then we'd have two possible. Either the true population average is indeed 2, and you just happen to select a strange and unusual sample, or the second will be our original claim of 2 is wrong, and we reject the claim and conclude that the true population average is more than 2, right? So what we can say that what we can conclude is might happen that the true population average is 2. In this case, if it is 2, then we must have taken some unusual sample. Must have taken some unusual sample. This is the first case. Second case could be that our claim of 2 is wrong. Our claim of 2 is wrong. We reject the claim, right? Reject the claim. And what we'll conclude? We'll conclude that the we'll conclude that the true population average is more than 2, right? So this can be the two conclusions. Of course, I don't raise an example simply to draw a conclusion about the frequency with which the list students attend concerts. Instead, I raise it to illustrate that in order to use a random sample to draw a conclusion about the population, we need to be able to answer the question, how likely? That is, what is the probability? Let's take another example. Suppose that a Delhi parking office claimed that two-thirds of the Delhi students maintain a car in the state college. Then suppose we take a random sample of 100 Delhi students and determine that the portion of students in the sample who maintains a car in this college is 69 upon 100. That's 0.6. That is 69%. Now we need to ask the question, if the actual population proportion is 0.67, how likely is it that we would get a sample proportion of 0.6? What I am saying is, if Delhi parking office says 67% of students maintains a car at college, and when we take the sample 100 Delhi students, right? We found it to be 69 upon 100. That is 69%, right? So how come that the actual population is claiming it to be 67%, and we would get a sample proportion of, and we get a sample proportion to be 69%, right? Then again, you have to think about this, that if the answer to the question is ultimately likely, then we have just one possible conclusion, that the office claims is reasonable and we do not reject their claim. Again, I don't raise this example simply to draw a conclusion about driving behavior of the list. Instead, I raise it to illustrate again that in order to use a random sample to draw a conclusion about the population, we need to be able to answer the question, how likely or what is the probability. So, dealing with this two example, we can summarize one. Why do we need to learn probability? Anytime we want to answer a research question that involves using a sample to draw a conclusion about some large population, we need to answer the question, how likely is it? Or what is the probability? To answer such a question, we need to understand probability rules, and probability models. And that's exactly what we'll be working and learning throughout this course. Now, we have got the motivation for this probability course. behind is, and let's delve right in and let's start filling up our probability toolbox. So to start with uh, this probability toolbox, the first thing that comes to our mind is the sample space. We have already seen we have already seen collection of all the possible outcomes. We have already seen the collection of all the possible outcomes, right? Collection of all the possible outcomes. Now, under this collection of all the possible outcomes, the first thing that comes while dealing with probability is the event. What is an event? Event is always denoted by the capital letters, right? If we have to define event, event is just defined as a subset of the sample space. Subset of the sample space. That is A is a subset of S. This thing, this is said as subset. This will be the abbreviation for subject. Subset, subject, not subject. So suppose we randomly select a student and ask them how many pairs of jeans do they have, and in case sample space will be, if I ask random student how many jeans do they have, sample space could be 0, sample space could be 0, 1, 2, 3, any number, right? We could theoretically put some realistic upper limit on the sample space, but who knows that what it would be. So let's leave it to accurate as possible. Now let's define some event. First event is E is the event that a randomly selected student have no genes, right? So event A is student have no genes. That is 0, right? B is the event that the randomly selected student owns some genes, right? So student owns some genes, right? So the number will be 1, 2, 3. Again, it will be any number. It can be any number, right? Okay, it can be any. Now, if we consider another event C, right, of a randomly selected student who owns no more than a 5 pair of, right? So the student owns no more than 5 pairs of genes. That would be 0, 1, 2, 3, 4, and right, right. We can consider another that they have odd number of pair of genes. So odd number 2, 1, 3, 5, right? So this would be the way we will define an event. Event could be the student have no genes. Event could be the student have some genes. Event could be that they own no more than a 5 pair of genes. It could be that they own odd number of pair of genes. So it could be anything, right? So events and sample spaces are just sets. Set theory we have discussed in our high school. So events and sample space are no more than a set. So uh, let me introduce you with some terminologies like this is phi and this is the null set, right? You must some of you must be aware with this. This is also called empty set, right? The other could be this, and this is denoted by union. This set to be as a union. That is the element. The element could be the element in C or in D or in both, right? We have to consider this. This means intersection. Simply means that the element is in element is in both A and B, right? This is also called mutually exclusive event. Exclusive event. But for this mutual exclusive event, uh, the A intersection B has to be equal to 0, right? If they are empty sets, right? So it has to be equal to 0. Then there is A complement, that means 1 minus A. Let me not write like this. A complement means A complement simply means element other than A, element other than element other than, right? Then we can use a case like A union, B union, C union, D. This is this is a case of exhaustive event. Exhaustive event. The name also suggests that all of them are taken, and this is also called sample space, right? Sample space. Wait for my handwriting. So this could be the case, right? So let's revisit to our previous question, the previous example, that how many student only games. Suppose we randomly select a student and ask them how many pair of jeans do you have? They can say 0, 1, 2, 3, any number, like, right? So let's define some composite event. This is called composite event. So the union of the event C and D is the event that a randomly selected student either owns no more than 5 pair of or owns an odd gene or number. So if C is like C union D is defined as the event that a randomly selected student either owns either owns is not more than 5 pair or or odd number of. One thing I forgot to explain you, uh, that is, here in the case of this union, keyword is or, and in the case of intersection, the keyword is and. Or means it can be in C can be in D, it can be in both. Any case can happen. And means it has to be in A as well as in B, right? Now we have a case where it says C union D is event that a randomly selected student either owns not more than a 5 pair or odd number of genes. So C union D will be equal to 0, 1, 2, 3, and it can happen as 4, 5, right? 7, might be that 6 will be included in, right? This will not be included because till 5 we have that. This is for the first case that they not more than 5. This will be for the first case, and in second case this was 1, 3, 5, 9, and then 11, right? So this was the first event. Now if we have to define intersection event, let's say A and B is the event that a randomly selected students on nowhere and owns somewhere, right? So that if we say it as A intersection B, that will be 0. First of all 0, event intersection with 1, 2, 3, some pair of genes, right? So the intersection between this will be a empty set of called as a phi, right? Now the complement of event D, if we define the event D as, first of all we have to define the complement of an event is event that randomly selected student owns an even pair. Why? Because D was the event that students have odd pair of genes. Odd pair of genes. So B complement will be the event they have what they have even pair of genes. Right. So D complement will be the case. It will be 0, 2, 4, 6. Right. So this way we can just explain the case. Like one case is left that is called exhaustive exhaustive event. Define exhaustive event. Let's define A as 0, 1, B as 2, 3, C as 4, 5, right? And D as 6, 7, right? So in case we have any union B, union C, union D, union, yeah, D, right? Should be 0, 1, 2, 3, 4, 5, 6, 7. And this is our sample, that is 0, 1, 2, 3, 4, 5, 6, and 7. Right? This will be our sample. So this is called the exhaustive event where nothing is left. Now we have seen uh, why the probability is needed. Wherever we want wherever the question raises how likely it is to happen, how likely is the case that it will happen. In all the cases we need to know what is probability. So if we define probability informally, right? If we write a formal definition for the probability, we'll write the formal definition. Let's define it informally for a moment, and let's see how we can define it. Like we can say probability written a wrong spelling. Probability. Friends will kill me writing this wrong spelling. Right. So probability informally can be defined as a num which is between 0 and 1, right? Could be like a number close to 0, the case of not likely to happen. We say that there is a 0% chance of rain today. Simply means that it is not likely to happen today. Third case will be a number close to 0, sorry 1, and this is a case of most likely to happen, most likely, right? This could be the case where someone predicts that rain will be today, will rain, right? So this could be informal definition. I will say that it's a number between 0 and 1. When it approaches to 0, it is not likely to happen. It approaches to 1, it's likely to. Now, can you think of an event that cannot occur? Can you think of an event that cannot occur? And can you think of an event that will definitely occur? Let me explain you with an example. Let's take an example of an event that cannot occur. That is 7 in rolling of dice. When 7 come in the rolling of dice, right? Right? If you take an event that today sun will rise in west. Today sun will rise in west. Cannot happen, right? Sun will always happen, always rise. Sun always rises in the east. Cannot happen. So these are the cases where we can say this is the event that cannot occur. Let's take an event that this will definitely occur. Same example, sun will rise in the east, right? This will be an example. Like if we toss a coin, we say there is a definite chance of getting a head or a tail. Obviously, it's a definite case. We get some value. Now, how to assign probability to events? We know that the probability is a number between 0 and 1. How does an event get assigned in a particular probability value? There are 3 ways. According to me, there is a 3 way. First could be the personal opinion approach, right? So this personal opinion approach. Second could be relatively frequency approach. Third, with the classical approach. Right? By personal opinion approach, I mean the approach is the simplest in the practice, but therefore it is also least reliable. We might think of it as whatever it is to, be, to us. So it's not a reliable approach, right? Like I think there will be 80%. I think there is an 80% chance for rain today. I can also think there is a 50% chance for rain today. I can think there is a 50% chance that the world's oil reserve will deplete by year 2100. I can also think there is a 1% chance that our football football team will end up in final fours by this decade. So this could be the personal opinion approach, right? For example, if we say one day you will die, first question, right? You can also say you can swim around the world in 30 hours. You'll win a lottery someday. A randomly selected student will get A in the course. You will get A in the course. Like these all things have different things. So, like the first question, one day you will die. It is definite. It's fun. On the other hand, the probability that you can swim around the world in 30 hours is nearly zero, as is the probability that you will win a lottery sometime. I'm going to say that the probability that a randomly selected student will get A in the course is a probability between 0.2 to 0.3 range. And one thing I left on you is what do you think about the probability that you will get A in this case, right? So this could be a personal opinion approach. Now we can think of a relative frequency approach, and this is a relative frequency approach could be like if we if we perform this experiment maximum number of times, maximum number of times, let's say n, a number of times. We count the number of times the event A of interest occurs and calls it as a NA, right? Call it as a NA. The probability for the event A will equals to NA on N, right? Smaller, it will be smaller. This number of times the experiment has been performed. We are taking a particular case and count the number of times event A has occurred. So NA upon N. So this is a relative frequency approach. Like if it's a question like uh, what is the probability of getting ahead, right? And if I toss it 4,000 times and I get 2,000 times, 2,048 times, probability will be somewhere close to 0.50 sometimes, right? So if n is 4080 and event that I have the head is given for the head is 204n, so we'll simply find the probability of A that will be 0.48 upon 4080, and this will be equal to 0.569, right? So this is close to 5. So as we can say that relative frequency approach is a pretty good approximation to 0.5 probability that we would all expect of a fair. Perhaps these examples also illustrate that the large number of times an experiment has to be conducted, right? To get a reliable result, we have to perform it large number of times, right? So there could be many examples. So what is the probability that the one tree selected at random is a disease? But we have to take for that up some questions. But the classical definition, or you say the classical approach of defining probability. So the classical approach is the method that we investigate quite extensively in the next class, right? And we define the probability of event as P is equals to NA upon S. NS is the NA is the number of element, number of in event A, right? S is the number of elements in the sample space. So this will be the classical approach that we will do in the upcoming questions. Like let's do a question first, then we will define what is actually probability. Suppose we take a standard deck of 52 cards, right? And we recall that there is 13 faces. You know it. It is ace, 2, 3, 4, 5, 6, 7, 9, 10. And there is a jack, king, and right. 13 faces are there in 4 different suits. That is club, again club, and diamond. It is heart and spade. These are the 4 different suits. Right. Our question is, event we define over here is we get x is 2, 3, or 7. Right. So probability for this will be 12 total, because each 2 will be divided into 4 different suits. So 4 into 3 divided by how much? 52. This is the event A. Event B could be, if the event B is, like if the event B is set that X, we get 2 of a heart, right? 3 of diamond, 8 of spade, and king of this club, right? We have to define like this. This could be the case. So for this, what is the probability of B? Probability of B will be 1, 2, 3, 4 cases. So there will be 4 cases. 4 of 152, 1 of 130. If there is a question that that the card is either 2, 3, 7, or 2 of heart, 3 of diamond, 8 of spade, and king of club, right? So let's count the total event. Like in the first case, A was equal to 12. That was equal to 12 event, 12 cases. 12 times. And since 2 of them has been included, 2 of heart has been already included, the 3 of time. So 2 are left. So we will occur 4 times. A intersection B is 2. Right. So if we have to ask, we are asked what is the probability of A union B? Right. That means all of this will occur. As we will 12 cases of this and 2 left cases, that will be 8 of spade and let me use the other color, 8 of spade, this 8 of spade, and this king of club, and the other 12. Total will be 12 plus 2 upon 52, that will be equal to 14 upon 52. Right? If it is asked, if we are asked another thing, that is the A intersection B. A intersection will be the 2 cases, the 2 of heart and the 3 of diamond, that is 2. Right? And if we calculate the probability of A intersection B, it's equal to 2 upon 52. Simple. Now, let's define probability formally. Right? So, or do one thing. you people try to do some questions without knowing the formal approach of probability. There are events. For the probability of event, we can define some things, but let's do one thing. You people first of all try to do questions by your own using any question and in expanded form, right? In the most informal form you can do. And after that, in the next class, we will define probability in next session. We will define probability formally, right? Like we will define what is the probability of an event. We will take multiple examples. We will define its uh, theorems. We'll also define its theorems, right? So we will do that in our next class. So today we have discussed all of this. So in next class, we'll surely discuss all of this next thing, that is we'll discuss formal definition of probability and the theorems, right? Thank you so much for today. We'll do it in next class.